In question 4, we are asked to determine whether or not this vector is in the set, in the span of these other vectors, where the vectors are polynomials of degree at most 3. What this is asking is, does there exist an does an A, B, and C in R such that A x cubed plus x squared plus B x squared plus x plus C x cubed plus 1 equal x cubed minus 3x plus 3. And the way to do this is what we can do is we can just expand and collect, and we're going to compare coefficients to create a system of equations. Well, this would imply that A plus C x cubed plus A plus B x squared plus B x plus C equals x cubed plus 0 x squared plus 0 x plus, or plus, sorry, plus 3x plus 3, or sorry, minus 3x. Well, this implies that A plus C equals 1, A plus B equals 0, B equals minus 3, and C equals 3. And from here, we can build an augmented matrix. Consider the augmented matrix representation. 1, 0, 1, 0, or 1, 0, 1, 1, 1, 1, 0, 0, 0, 1, 0, minus 3, and 0, 0, 1, 3. And we could go to here and we could do our Gauss elimination and work our way through and get all of our pieces. And you could be super diligent to determine, okay, how can we solve this expression? Okay. And you could do your row operations, or you could see that B is defined here and C is defined here. So A equals 1 minus C, which equals 1 minus 3, which equals minus 2. And A equals 1 minus B, which equals 1 minus minus 3, which equals 4. But minus 2 does not equal 4. Thus, no valid linear combination exists. Therefore, x cubed minus 3x plus 3 is not in the span. Okay? Or we could do our row operations. R2 minus R1, replacing R2, gives 1, 0, 1, 1, 0, 1, minus 1, minus 1, 0, 1, 0, minus 3, 0, 0, 1, 3. And now we take R3 minus R2, replaces R3, gives 1, 0, 1, 1, 0, 1, minus 1, minus 1, 0, 0, 1, 2, minus 2, 0, 0, 1, 3. And we can see that we have an issue here. But to finish it off, we let R1 minus R2 R3 replaces R1. R2 plus R3 replaces R2. And R4 minus R3 replaces R3, giving us, or R4 gives us 1, 0, 0, 3, 0, 1, 0, minus 3, 0, 0, 1, minus 2, 0, 0, 0, 5. Well, this gives us the system x1 equals 3, or a equals 3, b equals minus 3, c equals minus 2, and 0 equals 5. And this is our inconsistency. This gives us no valid solution. Because there's no valid solution, we have an inconsistent system equation, so we're not in the span. We're now given a real vector space with vectors x, y, and z. Now, being told it's a real vector space, this tells me the field is real numbers. So this tells me R, that's my field. My field is the real numbers. Okay. Now I want to show that these three vectors are linearly independent if and only if. What I'm going to do is I'm going to, in the forward direction, assume if ax plus by plus cz equals 0, then a equals b equals c equals 0. Consider, and I'm going to do a bar x plus y plus b bar y plus z plus c bar z plus x equals 0. And I want to show that a bar equals b bar equals c bar to show that it is a linearly independent set. Well, then I can expand this to give a bar plus c bar x plus a bar plus b bar y plus b bar plus c bar z equals 0, which implies 0, a bar plus b bar equals 0, and b bar plus c bar equals 0. This is by or as set x, y, z is linearly independent. These are all equal to 0. So I'm going to solve this system of equations. So I'm going to look at consider the augmented matrix representation 1, 0, 1, 0, 1, 1, 0, 0, 0, 1, 1, 0. And now R2 minus R1 replacing R2 gives 1, 0, 1, 0, 0, 1, minus 1, 0, 0, 1, 1, 0. Now R3 minus R2 replacing R3 gives 1, 0, 1, 0, 0, 1, minus 1, 0, 0, 0, 2, 0. R1/2 R3 replacing R3. And because we're the real numbers, we're allowed to divide by 2. This gives 0, 1, minus 1, 0, 0, 0, 1, 0. And now R1 minus R3 replaces R1. R2 plus R3 replaces R2. And this gives me 1, 0, 0, 0, 0, 1, 0, 0, 0, 0, 1, 0, which means thus x equals 1, or a bar equals 0, c bar equals 0. And therefore, the set x plus y, x plus z, or y plus z, z plus x is linearly dependent, or independent. Linearly independent. To prove the reverse direction, we are going to prove the contrapositive. To do this, we assume that the set x, y, z is linearly dependent, and we want to prove
the set x plus y, y plus z, z plus x is linearly dependent. Okay. With this assumption that x plus y plus z is dependent, then there exists a, b, and c such that ax plus by plus cz does not equal 0, and at least one of a, b, and c is non-zero. Now here, we haven't assumed anything about the order of x, y, and z, or these coefficients, so without loss of generality, we can assume a does not equal 0. So what I'm doing here is I have a number times our first vector plus a number times our second vector plus a number times our third vector. And there's no reason why we couldn't relabel these, let's say z, y, x or something. So wherever the non-zero entry is, we can relabel it so that A is the non-zero entry. Okay. Now, consider a linear combination of x plus y, y plus z, z plus x. And we want to show that there can exist a non-zero constant. So we start with a bar x plus y plus b bar x y plus z plus c bar z plus x equaling 0. We want to show that one of these constants can be non-zero. And to do this, we're going to expand and get a bar plus c bar x plus a bar plus b bar y plus b bar plus c bar z equals 0. Letting a bar plus c bar equal a bar plus b bar equals y, and b bar plus c bar equal, or a, this should be b, and c, we see that we have equality to 0, and that a bar plus c bar is not equal to 0, which implies that a bar or c bar doesn't equal 0. Thus, a non-trivial linear combination equals 0. Thus, the set x plus y, y plus z, z plus x is linearly dependent. And we've proven what we want to ask.